Welcome to a video in curve fitting. You, in this group project, will be given an opportunity to fit a curve through data points that you yourself have coordinatized based on the object that you are trying to model. The purpose of this lesson is really just to discuss how to create a regression polynomial or several regression polynomials through the points that you are trying to make a model for. So let's begin. Let's imagine that you have successfully coordinatized and you ended up creating a table like this. So let's say you have your data points taken down, and I'm going to just step through this. I'm using Desmos. I will share the link with you at the end of this video if you want to also see how I wrote this, and if you want to use or reuse any of this, you are welcome to. So here what we have is one polynomial that I'm going to be trying to redo. And I used the table feature. I entered the data in a table, which is here. I clicked on this, and it would create, and then I entered in the various points. I have entered in the point 0, 0, 2, 2, 4, 3, 5, 2.5, 6, 1, 8, 1, 9, negative 1, 10, negative 1.5, and 12, 0. And what you'll see here, if we're looking at this graph, I'll go the other way, is you'll see these little green dots representing the various points. What we want to do is try to fit the best fit curve through this series of points. To do that, we'll use one of Desmos' features. There's also a tutorial that Desmos creates for this. And what we're going to do is, right now, the data points are x values are under x subscript 1 and y values are in y subscript 1. Whenever you create a table, it will create an x1, y1, or it'll create x2, y2, and so on, depending on the order that you have created it. What we're going to do next is try to fit a curve through these points. To do that, we're going to create a regression model, and this is going to go as follows. So let's create a regression model. When you're to do it, you go y1. When I type 1, y, and then I type 1 next to it, it will automatically make a subscript to it. I'm going to press a right arrow to go up. I'm going to use the tilde symbol, which is right next to the tab and 1 key. And that's telling us that we're going to do a regression. In order to do this in an efficient way, we're also going to use subscripts for our constants. So for example, I'm going to say C, and I'm going to do an underscore 0. And to do an underscore, again, I can either just type or type the number and it'll automatically know to go below, or you can also press an underscore character and that'll make it shift down. And I'm going to press right arrow to go back up. So right now that's not a great regression model. Let's go to C1 because that'll distinguish it. Underscore 1 and X. So right now, and then the thing is, X is just a generic X. What we're talking about is we're trying to regress it against the X1 here. So let's do that, underscore 1. You'll notice that it tried to put a straight line through these points. That does not look very much at all like it, so we're going to continue on. So we're going to go plus C2, underscore 2. And then again, it's against X1, underscore 1. But this time, and I press the right arrow, and then I'm going to go squared. So caret sign, 2. And now it's trying to fit a parabola through these points. It's better, but it's still not very good. Your r squared value is representing, it's still rather low. Your goal is to try to get it within at least 0.8 or higher. That's usually a good, a relatively good fit. Even 0.9 or higher is even better. But really what you look at is visually. Do you think this curve that you see here is currently a good fit? Probably not. So let's keep going. And each one of these, you'll notice it's actually telling us what the values are for C. So C0 is 0.9, and this actually represent, we'll talk about what they represent, but they are representing the coefficients for now. So I'm going to do C underscore 3. Let's go to a cubic and see if that helps things any. Okay, it's again still x1 cubed. That isn't terrible. Now it's up to you whether you think that is sufficient or if you want to keep going further. Still, it doesn't seem to be fitting to these points very well. So let's see if we can improve. And also it looks like it's missing these points, and it's missing some of these other points too. So we feel we could do a little better. Let's go to plus C4. C underscore 4 x1 to the 4th power. It certainly is improving a little bit. Our R-squared is going up. Now it's about 0.9065. This isn't terrible. It's still missing some of these points down here. But it is going through the 12, 0, and it is going through the 0, 0, relatively speaking. Let's go one more degree up just to see what happens. Plus C underscore. And the question is, well, when do you stop? When you feel it's efficient. At some point, it's overfit, and it's maybe not doing what you thought it would. So it really is, what I would say, a combination between art and science to know when you stop. Like right now, I feel I'm going to stop. There's not much we can do about this particular point, but it is looking like it's reaching down to these points. It looks like it's hitting these points. We will talk about how to resolve these two dots here, because those don't seem to fit, but overall it appears to be fitting. Okay, so the question is how to interpret these different coefficients. What you do next is you create a function and type it in very carefully. If you make an error, you'll know, because as you're typing in the function. So what I mean by that is I've taken these values, and in an earlier step I'm going to take some of these away because I was trying to hide it during the video. You'll notice that the C0, which was way up in the front here, and if we look at this again, our R-squared value is 0.9121. It's good enough. Looking at this, our negative 0.0322269 is here. That's our constant coefficient. Our coefficient for a linear term is here. Then the quadratic term is this one. The cubic term is this one. And the quartic term is this one, and it goes all the way up to x to the 5th power. Again, this is super careful typing. I would say probably this is where most mistakes are made, meaning one way to check to see if you got it right as you're typing it, those two should overlap exactly. That is your regression fit. So looking at this, you will not be able to distinguish between one and the other. If I turn this off, it is the same curve. If I do this, I'm looking at this, and I turn the other one on, you don't see any difference. What that pretty much tells us is that it was done right. And what do I mean by that? Suppose I made an error. Easy to say, maybe I typed 2 here by accident. So as you can see, making that one difference completely, it doesn't match up. But if I typed it right, the curves match up exactly. So that's an example of testing to make sure you wrote it correctly, because you will end up using this later on. If I'm only interested in seeing this curve from 0 to 12, I can simply turn this on. And now I'm going to use red and turn these two guys off. You're looking at the domain of the function, right? Because our point started at 0 and it finished at 12. It's not a terribly bad fit. It's okay. It's really a debate whether we could have fitted better or could make improvements, and we'll talk about how to make improvements on this overall fit. So this is one polynomial that fits through, or attempts to do best fit. It's the best fit polynomial regression along all these points. Okay. But suppose you decide to do it for 2 polynomials, and I'll explain what I mean by that. First of all, let's turn off the dots. And turn these off. And let's go to 2 polynomials with 6, 1 as a common data point. Suppose I took that table and I broke it into 2 parts, meaning I took the first half of the table and finished at 6, 1, and did like this, and make a separate polynomial for this portion. So I'll do that, and I go through the same process that was described above. So I'm going to turn this one off for the moment, because we're going to actually create 2 separate polynomials now to fit that. And then I actually stopped at the 3rd power. I felt that was sufficient for what I was trying to do. Looks like a very nice fit. The fit is actually perfect. When r² equals 1, it's 100% of a fit. And here are different coefficients. Now, when you see something times 10 to the negative 18, that's effectively 0. So our constant term is 0. And then again, going through the process of creating the function, I call it g of x in this case because it's a different function. And that is officially g of x here. And just to check that I typed it incorrectly. You'll notice this turns orange, but it is still on the same curve as the other one. So there's no differences. So that's reassuring. Okay, the next part is we're going to do the second half of the table from 6,1 all the way up to 12,0. Notice this point here is connecting the two. So you'll see it here in blue, and I'm trying to create a curve through this section. And so we're going to do that. And for the sake of this particular example, we turn the other curve off for the moment. So now we're looking at the blue. I'm going to create a regression model through that. It's not terrific. We could do better. But for the purposes of this, I just wanted to show you this. You could stop at a parabola and say it's done. Or you could have added more terms. Just for the purpose of this, I'm going to leave it alone. As you can see, it's not a very good fit. It's only 0.54. The other one was 100, was 1. This was only 0.54. So one might consider adding more terms into this particular polynomial. Now you might also find that this visually seems the best fit. Play around with it. Add more terms. Take off terms. See what works. So just as a quick check, did I type, after creating the regression model, I do a quick check to make sure I create a correct function. Looks correct. Notice the orange does cover over the blue exactly. So if we're looking at these two curves and we're going back to it, we can create, there's the blue portion going through, that was the first half. And over here we have the model here. So those are two functions. Now this part did really well. This part could maybe be improved a little bit, but again, this is just for the purpose of illustrating how this works. In other words, we could have done maybe a better polynomial regression than the one you see here. Now what's interesting about this is there is a slight disconnect here. In other words, they're not connected at what they would call a knot on a function, where the knot is where you're stringing different functions together. There are processes that would actually help these connect. That is beyond the scope of the course, but it is introduced when you're trying to do splines or Bezier curves. So let's take a look at what we have done so far. So far what we've done is we've taken the regression through all the points, making a best fit regression polynomial, which looks like this. We've also taken an approach where we broke the data into two groups using a common point of 6,1 and creating a first function and creating a second function. There is debate whether that second function is really a good fit or not, but again, I am sharing this particular app with you so you can also make improvements upon the model. There is also a way to improve the model, which will be discussed a little bit later in this video. So let's take a look at the volume of revolution for this one polynomial right here. And to do that, Desmos does do integrals. F of x was that function which defines effectively the radius from the axis. So if you take pi f of x squared, that really is using the disk method to find the volume of revolution, or volume of rotation. And that comes out to 108.677 cubic units, whatever the units happen to be in this context. However, you can also do a volume of rotation, one for the first function, one for the second function, meaning, let's take a look at this one instead. So if you're looking at a volume of rotation for two polynomials, what you would do is find the integral for each part of it and then add them together. So we would do it for the first one, we could do it for the second one, and then add the two parts together. We'll call that volume 2. You'll notice that the second estimate is much lower than the first estimate, which was 108.677 cubic units. This one is claiming it's 94.448-ish cubic units. And again, part of that might be because this curve here, this polynomial regression curve, maybe doesn't scoop up as much area as the other one did. So when we look at that, so as you're looking at volumes of rotation, that would then imply that there's less volume in that particular slices. Okay, let's improve upon this model, because looking at either of them, they don't seem particularly good. There's a debate whether you think the first approach or the second approach is better, but let's work upon that. So The part that was not very good, or one that we're not particularly happy with, is this second portion of the curve. So let's, for the moment, hide those. And consider the part that we felt was good. Now notice here, this seems like a straight line. So one might interpret that if you have if you're thinking of a function, right, or maybe it's an object, it goes, then it has a straight component, and then maybe something else happens here, and we could model it with that instead. So if we choose to do that, here is a possibility. There's our g of x, which is defined to be that first function. We'll let this first one just be 1 from 6 to 8. And then we'll find a separate function that takes care of the remaining 1, 2, 3, 4 points that would fit through here nicely. So let's improve them on the model. That's what this is called. Again, just to highlight, we're looking at the points that just turned red. So again, just a quick, right, those blue ones that you see on the right, now I've turned into red. This is what we're going to be focusing on. As we look at this, working through the model, again, this is x4 and y4. So we're going to add, it turns out that a parabola is a pretty good fit if we were to work through the model. It's nearly a perfect fit. It's the r squared is 0.99. So that seems good enough to stop. Again, you don't need to overfit a polynomial. You just need something that does a good fit. And so in here, simply typing in afterwards, we'll create a function called j of x. And now you begin to understand why I was defining functions, perhaps, is because that the function itself now is very easily usable, like, for example, making an integral. And so what it is if we just want to focus on the small component of this, so j of x is the same, you can tell because purple and green do overlap without any error. Again, it is very easy to tell if you made an error. Supposing instead of writing 52.9818, I wrote 42.9818. You'll notice that they don't fit. So again, having the regression graph on while you are typing in the function below it is a good method to make sure you did it right, because you end up using this j of x as your function rather than typing in it from scratch into the integral. That's just a helpful tip. So in here, I'm going to keep the j of x part from 8 to 12. I'm turning that portion on. I'm going to just turn the whole thing off and just keep that one on. There's the part, so that this full function is made of 3 pieces. They seem like reasonably good fits for the data that was points that are plotted. Lastly, what we can do is the volume of rotation would then be made of 3 components. And so what we're looking at here is I'm going to call volume of 3 part 1, volume of 3 part 2, volume of 3 part 3. Those are the integrals. The integral in the middle has a effective radius of 1, which is then squared and then pi, so that's what this part comes out to be. Add the 3 parts up, and the volume is approximately 112.62, about 8-ish cubic units, whatever the units happen to be. If it could be cubic centimeters, cubic inches, cubic feet, cubic miles. We do not know what scale this graph is being taken from. Just as a quick highlight, if you're trying to imagine like what does this look like, a 2-dimensional representation of this rotation would look something like this. This is the 2-dimensional one, and I did use different shading to show the different 3 functions that were integrated. So you're imagining this whole volume being rotated, and that's what you get. That's just a quick breakdown of how you use Desmos as a tool to not only do regression, but it also can do integrals. It actually does it pretty well and quickly. I'm going to leave this picture up just for the moment. So what we have is Desmos can do regression. Now there are other tools out there which also do regression. You might be saying, well, can I get the numbers even more precise? The answer to that is yes. There is a way to do it. There is a utility called the Polynomial Regression Data Fitter. It's at arachnoid.com, polysolve. Again, this link will also be shared as well, so you can use it if you wish. All you need to do is take the points that you have and simply cut and paste it. So like right now, what it defaults to is it'll be some other data set that you have here. Here's an example of some data, and then you can change the degree as you wish to fit the polynomial to as much as you want. And this is 6 degrees is the most you can do. But looking at this, probably fourth degree would fit this particular data set well. Okay, I'm going to go back down to 2 again. And so let's imagine that we wanted to do, let's say we want to do all the points. So what you need is some sort of a text editor where you cut and paste it, so because it's much easier to do it from that. So you have a text editor. So these are the points. And then what I'll do is I'll take this and then make that into a text. So I'll do that. And so here's the text version of it. And what I mean by making into a text, make sure if it's in a formatted font, you want to make sure that you take that part out. For my example, my text editor, I can turn something into plain text by simply clicking. Format, I can make it into plain text, and that is what I did over here, and that's what's saved in this file. Then you can simply copy, paste, and you'll notice it immediately adapts. So let's look at this. Still trying to fit a secondary curve. What's nice about this one, it's interactive. And you can go like this. That doesn't look so good. It's a little bit better. That's actually where we did stop, was the fifth degree polynomial. But you can go as much as you want. So I mean, we can go more, and it did something like that. So I mean, that would be like an eighth degree polynomial, which fits every single point. But you would have to decide whether this is truly representative of the situation. Notice it does tend to exaggerate the points here, so we do lose. Yes, it fits for all the points. However, you begin to lose some of the shape that is with it. So it overfits is what we'd call it. So over here, seventh, maybe not such a good fit. Sixth, it's okay-ish. This one seems to approximately resemble the shape of what we were trying to do. That's why we ended at 5. In order to now take advantage of this, let's say you say, I want to now use a numerical calculator to integrate this. This does use scientific notation. And you'll see some commas here, and you'll say e negative 2. Well, that really means times 10 to the negative 2 times 10 to the, at this case, to nothing. So that means it is what it is, exactly the right one. This is to the negative 1, which means it's times 10 to the negative 1. So the e notation is being used in that regard. What you would do is copy this. If you remember the coefficients from the Desmos example, they are the same coefficients. We would have to adjust it. So what's what we're going to do next? And so I'm going to cut and paste it, and I did over here already. To make the adjustments, what we would have to do here is move the decimal place over 2 places. You don't need to move the decimal places any places here. And so I'm going to do that, and then I already did that portion over here. So let's say I do that. I'm going to show you that work already. Done. So here you have the coefficients that have been put in now in standard form. What this is negative, positive, negative, positive, negative, and this will be positive also. So what I would do next is, this is our constant term, this will be our x term, this will be our x squared, our x cubed, our x4, x5. So what I would do then is, just put it through. This one's x, this one's x squared, this is x cubed, x4, x5. And then we just simply put them together like this. And that is actually how the function itself. There are several things we can do with this function. We can put it into an integral and see what comes out. If we remember our integral, it was in Desmos. Let's just take a quick look at what we had. So this has a few more digits than Desmos did. And if I remember that, because that was that first one, so we're going to look up our first fit. Following rotation for the one polynomial was 108.677. Okay, so that's just what we got already. Let's take a look, and we can use something called WolframAlpha. I will put that link also up in the example. But let's see, we want to do integrate pi times this whole function. So what we're going to do is we're going to take that function that we have now in the text editor, copy, paste, okay, it's squared, dx from 0 to 12. Oh yeah, and it's in the variable of x, so we should say that too. So x equals 0 up to 12. And let's see what comes of it. Okay, it's thinking. 108.677. Looking good. So that does match what Desmos answered. It's still working, and then it says standard computation time is exceeded. Try again with pro computation time. Oh, that's nice. So they're trying to upsell Wolfram. That's funny. Well, let's just see what Desmos gives us just for the heck of it. They don't have such demands. So if we wanted to do this using Desmos, what we could do, let's call some other function here. See, we had j of x. I don't want to use, maybe k of x equals, let's use that really long function that we just pasted. Looks good. It actually took all of it. It did not complain. That's wonderful. And to do an integral in Desmos, because I didn't exactly explain how that's done, I type int, it will turn into an integral symbol. You can also use the miscellaneous under functions and go under, I believe it's misc, and you can also do it this way as well. I just know the shortcut is int, that'll do it. The lower limit is 0, the upper limit is 12. I'm going to do pi, and then the r squared, in this case the r is k of x, quantity squared dx. And the computation time on this one was never exceeded, just did it right on the spot. Thank you, Desmos. So maybe Wolfram is overrated when it comes to integrating, who knows. So looking at this, got 100, so we had it with a few more decimal places of accuracy, the regression. Got 108.6772333. The original one was 108.6774228. So it's actually pretty close. The regression was not as precise when done with Desmos, but it's really, really accurate considering the magnitude of the difference. It went out many places. The other one went out many, many more places. But when we're looking at the magnitude, they actually agree to the third decimal place, if I am correct on that one. Let's see. I'm looking for it. I know it was here. There it is. Yeah, they agree to 3 decimal places, which is pretty good considering the magnitude of the integral itself. So that's a short demonstration of how to do integration with Desmos. Also how to get polynomial regression through Desmos or the alternate tool. The alternate tool is a bit more precise, but you're going to need to convert the scientific notation into a standard notation in order to use it appropriately. The only other tip I would say is that if anything is a very, very small number, like in the case where we had 10 to the negative 18th, consider making that coefficient a 0. You're not getting much bang for the buck by adding that in. You might be just using up computing power. And that's kind of a quick synopsis of how to do it. I hope you found this video helpful. I will share the links of not only the app that you see here, but also the polynomial regression tool. And if you want to try integration through WolframAlpha, you definitely can also do that. I will share that link as well. All right. Good luck on your project. I hope you enjoy it.